consensus authoring. I'm really excited about this. Consensus gets me really excited. The reason why it gets me excited is actually you don't need to be super technical to get it. Actually, I feel like you could explain the really in-depth research stuff of consensus to somebody who has like basically no math background, and as long as they can follow the intuition, then they can kind of get it. That's taken words from somebody who's very, very deep in the consensus research. Specifically, there's multiple parts of consensus, but today right now we talk about authoring, and Joshua will talk about this finality thing tomorrow, and we'll do stuff. So the way I like to explain consensus in generally, I guess I can go to the next slide. Yes, a decision-making process that achieves or strives to get some acceptance by the participants in some kind of system, right? Like your friends, we're gonna go. There's a nice example. I don't want to bust on that one, but yeah, there's we all need to get some kind of agreement sometimes to make decisions, right? And that's really what the whole consensus thing is about. The way I like to think of it is, well, I already forgot that thought, so we're gonna go to the next one. Maybe it'll come back to me. Blockchain consensus is reaching agreement. We talked about just reaching agreement, but we're gonna reach agreement over a shared history of a state machine, and that's what our goal is as it pertains to blockchain, as opposed to just consensus without blockchain. So it'll be very relevant to recall from the morning what we learned about state machines, and we'll expand upon that. I guess this is another block space. We talked about block space, but this is a nice way to kind of think about it. Is that consensus systems which come to agreement on if you think of a consensus system as all the participants, them coming to agreement on something about the state machine is kind of like this valuable resource that we're offering to people, which is like this block space. So you get your opportunity to have your state machine or your state of your application, whatever, verified and agreed upon by the participants in some kind of system, as opposed to just by yourself and saying like, this is my thing. You can get this kind of public validity. And so if the consensus system is strong and it has a few of these properties, which we'll talk about, then it's more valuable block space. And we talk about a few different blockchains and what maybe we think that their value of, if I have like a blockchain with Joshi and it's just us and we're like, hey, we'll sell you our block space. You might be like, yeah, who cares? Like, I don't want your block space. But maybe it's like Bitcoin, right? Ooh, ETF. So that means the ETF got approved, and so that means that different consensus systems have different value when it comes to block space. Let's make sure. Just got log notes. Yes. Okay. Well, we talked a little bit about forks, and this is actually what was from the last lecture. But in general, in these consensus systems, there's going to be people who have different opinions, right? They're like, this is an opinionated thing. And you could even say that every fork that we are even following on any chain is actually the opinion of most of the nodes. That's what our goal is. And so there may be other forks, and it's like, well, why don't we follow them? And we have rules. Well, we have things that we pay attention to for why we value certain people in the consensus system's opinions over others. So yes, so we call this like fork choice that we choose, the canonical chain, the one that we kind of agree on is the most valued opinion of the consensus system. There we go, yes. Okay, 5 aspects of consensus. They're not the only ones, but I mean, these are kind of like what we generalized. So state machine validity, this is like, we will go into it, but basically the state machine, this thing that we're kind of managing, I like to think of it as a database that we're all kind of coming to agreement on. It needs to have some, it needs to be valid in some way. And I'll I'll give you an example from the blockchain from scratch in a second, but or maybe we could just, yeah, I don't want to stop at that slide. That's one. The next one is there's maybe just some arbitrary rules that we set, that most people decide like, okay, and the reason I say most people is we have these things, hard forks probably, which some people have thought about or heard about, and that's basically just like a differing opinion on the chain. So, and maybe the reason that some blockchains had a hard fork is because some of these kind of arbitrary or political or decisive things that most people wanted for the network. But there's going to be disagreement. That's kind of the moral of the story. Authorship throttling, kind of like this word. So the whole thing is like, we're talking about this idea of producing a block or producing something in the consensus system that everybody's going to basically listen to, right? And so like, who do I listen to, right? Does everybody just post all their stuff? And then how do I sort through it? How does one sort through what I should listen to and what we shouldn't listen to? So we create some rules about who can post something that in a particular time frame, which we're going to listen to. Maybe it's not a particular time frame, but maybe they've solved a certain equation, or maybe they've done something, and we say, okay, I'm going to listen to that person, and we will advance our state machine accordingly. So it's important to have rules around that. Fork choice heuristic. So I said that we'd have differing opinions, but there might be actually like some more objective, kind of quantifiable things. If you've ever, yeah. So we'll talk more about that. There's different things which we use like just heuristically to choose what opinion that we care about. And then finality, which I'm not going to talk about at all, actually. So Joshua will talk about that. But yeah. Okay. So the first one, state machine validity. So this is just kind of like, I don't know, I think pretty intuitive. So it's like in the light switches example, it's like you can't go from off to off, right? So if somebody posts something saying like, we're going to go from off to off, you just basically be like, well, that's invalid. Like when you just like mashing the light switch, it's still going to be off. It's not changing the state at all. So we don't want to like, we create these kind of rules. Or maybe you can have a negative balance, for instance. So, we have these general like little box that we box our state machine into. That's important. Good. All right. Good. Everyone's getting it. Don't mash the light switch. Okay, this arbitrary political validity. So what are some examples of that? So in some blockchains, maybe I guess in Bitcoin, right? Sometimes people, some people had some, does anybody know this like big blocker, small blocker thing? Has anyone heard of that with Bitcoin? Oh, really? Nobody. Well, there's some, okay, one guy. 2 guys, 3, okay, 4, 5, okay, 6. So we talked about in the state machine thing, like this idea of like having this block size, and Josh, you talked a little bit about like, we talked about gas metering and stuff like that, and what does that mean? And there's an opinion, basically, long story short, blocks have transactions in them. Transactions actually advance our state machine in some way. And so if you want to increase the throughput of your system, it'd be nice if you could process a lot more transactions in a single movement of the state, right? And so some people wanted to make maybe Bitcoin faster and be able to process more transactions in a particular block. So they had an opinion that maybe we should change the block size. And so this meant that there was some divide in the consensus participants that like, oh, actually we want blocks to be this big. Now, like everything in Bitcoin, unfortunately, these people always disagree on everything. So yeah, some people didn't want that. They're like, the traditionalists, the conservatives. That's one thing. Blocks that have hacked transactions. So there was a DAO hack with Ethereum, and There was a fork because of it, and people basically thought it was pretty bad for the network to have this kind of exploit in there, and well, exploit. So, anyways, maybe we decide that we don't want to listen to this one particular contract and what it does, and we're going to just throw away all the transactions that interact with this one smart contract, for instance. So yeah, that's something that participants can do. Empty blocks, I don't know, like totally useless. So why, we're just going to create that rule. Maybe a block with even state roots, something like this. So I don't know if this is just an image here, but. Huh? What is even state root? Oh, like, so the state root, maybe it calculates to like an odd number, right? Because the state root is a hash is a number, and so maybe we want the number to be even. Right? Yeah.
Thank you. Referring to the previous one, state machine valid, whatever. If you refer to empty blocks or block with even state roots, what's then the difference between the previous one?
Well, I mean, I'm just trying to categorize. One of them might actually not invalidate the state machine's logic at all. Like in terms of that, it might be just like, for instance, these a bigger block. That's not invalid for your state machine, but maybe people have just chosen that they don't want blocks over a certain size. Oh, okay. You're just saying for the empty blocks. Yeah, I think that you technically, in most cases, could submit an empty block. It's a valid thing, but it's just it's wasting our time, our consensus participants' time. So we just think, yeah. Okay. Next. Authorship throttling. Nice. This is a bunch of forks. Stuff's happening. Yeah, so really the question is like, why do we want to stop that? Maybe I'm answering the question for you. We really want to know who we should listen to. It's just, there's too many people out there, too many bad actors too. Again, this is kind of going to this thing. For consensus especially, we're going to think about the bad guys. Because the bad guys are going to want to trick our consensus system, and you'll see why. Because then you can maybe do some mischievous stuff and give yourself more monies, or you can like totally troll this chain or whatever. And so it's important to know, like, these rules need to be really well defined. So I guess I'm kind of answering the question here. Someone like itching their head, or? Okay. I don't think I can continue if you do that, but. Okay, cool. Cool, so we want to, so that brings us to leader election. So this is an idea that's in a lot of systems, not just blockchains. We elect the leader. Who are we gonna listen to? And there's many ways to do this. We're gonna talk about a few of them. So yeah, it says here we elect a small set or maybe a single entity who can author at a given time. Yeah. Oh, okay. I said that. And we say like electing the block producer and blah, blah, blah. But this is like in a more researchy context, a more traditional distributed systems context. A lot of people know this as leader election because people didn't care about blockchains or blocks. So I did have a question. So I said here that we would elect a small set, or ideally a single entity, who are allowed to author the next block. But we talked about I guess my question is, wouldn't it be easier if we just elect the same person all the time and they just always tell us? Like, why do we want to even like elect people? Like, wouldn't it just be easier to like listen to one person? Sure.
We'll get his, like, it will always be Putin.
It'll always be Putin.
Yep.
Oh, okay. Didn't know we were going political, but we did talk about politics a little bit in the slides. Sure.
For randomness, so that we can't know who is the next one and he cannot mess with the transaction.
Yeah, but why do we need a next one?
So if someone is always there, the same person, then he's really the centralized system kind of. So he will always be deciding which transaction to include, which transaction not to include, and messing around.
Okay. Messing around. Yeah, that's pretty much almost there. I'll just take one more. Is that? Oh, hold on. I know you can shout.
It will not be as safe because basically those leaders we cannot trust always, and if they know that they will be the same one every time, they can change the state or do some mischievous things.
They can't really change. I mean, they still could change. They still have to They still have to change the state correctly. So that isn't really the issue. He alluded to a little bit. Sure.
I think they would extract all the value because they can pick the ordering of transactions. They can pick who they censor, and essentially they're the only ones that pick the future and reality.
Okay. So yeah, that's pretty much it. Did you have anything else to add to that? Yeah. Oh, okay. I can. Oh, okay. I'm not gonna jump off stage like Josh did. Oh, okay. I'll try next time.
If the leader is predictable, it can be easily attacked by the OS, for example. So it's easier to attack the network.
And we're gonna go on to that in the next slide, which is perfect. But yeah, so I'll talk about that. I'll address that in the next slide, and but that's correct as well. Okay, so the answer is basically that we talked about the fact that we have this off-chain transaction pool, right? And basically, we talked about peer-to-peer networks yesterday, and when we basically what happens is you submit a transaction, and it gets got to some kind of node. Hopefully not just like some RPC provider who super centralized, but let's just say you do. These transactions get gossiped around the network. And so in general with blockchain, since these things are off-chain, you can always claim the block builder has the power of how they structure the block and which transactions get in. So it's a big concern if it's just one person and they really hate Joshi, and Joshi keeps saying like, please include my transactions, and it's just like, no, I hate Joshi, so I'm not going to include any of his transactions. So that's a problem, right? It's like biasability with, censorship resistance is something that we really, really want. And so, yeah, that's really, I guess, like kind of the main point. And someone mentioned like extractable value. Yeah, like maybe a lot of these transactions really, I can craft them such that I want them to benefit me, and your transactions don't really benefit me so much, so I don't really care. So it's important that we kind of rotate and spread the love, Cool. So next thing, which this nice gentleman in the front said, liveness. So we want the system to keep going, right? We don't want any Solana moments or whatever. Like we want this thing to like continuously never go offline, because we want to continue the ability for people to use this system in order to, run their applications, so to speak. It's not very helpful if like Google goes down, right? It's like, I got to Google stuff now, so where are you? So we want to keep the system live and we want to keep it operational. So if there is one guy, I mean, maybe I can just take him offline. And this is kind of the issue that we get in with like some centralized Web2 infrastructure, is like a lot of people care about listening to a particular server, and then some guy's like, cool, let's take that server down, And so that kind of sucks. That like makes our lives harder, because like we like when services are available and secure and able to work when we need them to work. So we want to be able to keep authoring new blocks. There's also kind of another, so I talked about like higher quality block space, and so a system that's able to be live and not go down, that might be a system that you would value for more for like their block space is much higher, right? If you're just like intermittently going out, it's like, I don't know, how valuable is it to get a transaction into your block, because it might not even go through. And certain applications, as you probably know, if they go down, it's pretty detrimental, especially in finance and stuff like this. It's like kind of a big deal, right? Like, oh, my money's trapped. Cool. Okay, does it go like that? Yeah, it does. So proof of work, nice. Let's get some people worked up. So this is kind of the, Bitcoin thing, Satoshi, and we talked about what the mechanism is when we talked about how to select what the problem is. So you're basically trying to do this pre-image search on SHA-2. And this is a way of doing the authorship throttling, right? Not everybody can find the partial pre-image attack for some hash with a certain number of leading zeros instantly, and everybody can do it like right away and submit. So there's some, this is this idea that we call proof of work. Okay, so what are some pros? Permissionless. So this is a property that we want, right? We want people to just be able to freely join. We don't want to block out certain parties. I mean, I don't. Maybe some people do. Or so we thought. I like this kind of side thing. Does anyone know why it wouldn't be permissionless, maybe, to do this proof of work thing? Okay, so he said hardware requirements. So yeah, like if I need a super cool, fancy computer that costs a ton of money, is that really that permissionless? I don't know. Like maybe someone who doesn't have that capability to get that hardware can't join the network as freely. Sure. Huh? Okay, yeah, we're gonna just need a mic.
Yeah, Mauricio, I'm saying like it is still permissionless. Like no one's stopping you from joining the network. It's your own lack of money. So no one in the protocol, no one in the consensus stopping you. It's you who's stopping you.
Okay, yeah, that's an argument. Okay, that might be a little bit more philosophical than we'd like, but it's like, I might say that that's kind of like, oh, I need like $1 million to join this club. It's permissionless, bro. You just got to have $1 million. Like, why don't you have it? Right, yes, okay. And this is the argument, right? So like, okay, technically anyone can join who has $1 million. So, yeah, permissionless for the few. Yeah. So the only thing stopping you is this resource, right? Oh, sure.
I have a question from previous slide, that when we say high quality block, why don't we say correct block or valid block? So what do you mean by high quality block?
I block space. So again, let's think of block space as the ability to get your application's logic or maybe your state machine, depending on the model of the system, verified by the consensus participants. So if you want to choose a system which can verify your application or your state machine, you might want to choose one that is pretty sound in terms of these properties, right? Like again, if liveness isn't a property of the protocol, of this consensus protocol, then it's not that valuable because like my stuff's going to go down all the time. Like I need my system to be up and operational for my users.
So that has to be
correct. I will say this too, sorry. I'm going to do one, so we'll have one question and then I'll answer, and then we can do one follow-up and I'll answer, and then that's it. Nothing against you, but I've noticed this kind of trend. Yeah, I'll do your follow-up. Yeah.
So I wanted to understand correct versus high quality. When you use high quality means there are any features which we want to ensure.
Yeah.
Apart from the correctness, like it should be related to the previous block and other properties.
Right. Yeah.
I'm not understand.
Okay, is that good? My answer on the high quality, or do you still?
I'm still confused. So.
You're still confused. Okay. Let's say I want to build my application on a specific chain, specific place, and what happens is there's a ton of forks, and they don't have a good way of selecting the authors, and the chain just goes down. So my application's completely paused. Is that a good thing? Yeah. Okay. Not a good thing, but thank you for your question, by the way. You asked good questions. Yes. Just want to be encouraged.
Hi.
Here.
So higher barrier to entry in terms of money or something else is not equal to permission less or permission with. You know, permission is totally different. Either you have to ask somebody, can you get in, or a criteria to get in, right? But then that's not like, it's not the same thing in any respect, philosophical or non-philosophical, right? Like if it's $1 million, let's say it's a club, right? And then you
Yeah.
need to be a couple. And then,
I think
or-
it's definitely an opinionated thing. Like, I think what's purity and permissionless? Like, literally, it's just the barrier is like almost nothing to get into the system, right? But there's like a spectrum here. It's not really black and white if you think about it. But again, this is kind of crawling down a more philosophical.
Not really. See, 19-year-old
Okay, this is
should
number
not.
2. So.
Yeah, 19-year-old in Canada cannot enter a pub or an alcoholic restaurant or something like
Right.
that, right? Like below that. So we
Sure.
do fake IDs and stuff, but that's okay. That
Right.
no, it is not. It is permissionless. Anybody above 19 can enter.
Okay, so I'm going to challenge you right there. Just stop you right there. So you said anybody who's 19 can't get in, right? But then if you can afford to buy a fake ID, you kind of get in, right? So there's a little bit of a barrier, or there's a little bit of, that's not fully permissionless, because like I can kind of cheat the system a little bit. But again, we're going philosophical, but I appreciate your discussion, and yeah, I'm going to move on. Cool. This always gets people really excited. You know? I want to bash on your Bitcoin. I own Bitcoin, so. All right, so it requires an external scarce resource, energy. So I need, like, if I want to run these, I want to run this algorithm to do this pre-image search, I need energy. I need something that is not just completely infinite. And so energy is a resource constraint. That's good. In some sense. We'll talk about it. Blind. So nobody knows the next author until the moment they publish their block. Somebody over here mentioned that, okay, well, if I know the next person who's going to author a block, I can do bad stuff to them, right? Does anyone know why I might want to do bad stuff to them? Like, why would I want to be, do bad stuff to somebody who's the next author? Anybody know? Okay, so someone said so you can author yourself. I think everyone kind of, so yeah, like I'm selfish. I want all the money, right? And so that's pretty much it. You have your hand up and you look like you're.
Oh,
So if it was just one person, we could potentially DOS him, and then we would like kill the liveness of the network. And how we could benefit is if we essentially shorted that chain.
I mean, a lot of ways to craft a nice financial game for yourself, right?
Yeah.
Many ways.
Yeah.
So it's good if we don't know who's going to come up, and we'll talk about like a few of the consensus authoring schemes that we have, include our latest one, which is being implemented in Polkadot. I'm excited to talk about that one. And so blindness is a really nice property for consensus. Okay, so expensive to author competing forks. So this is kind of going, wherever Jonas is, but this is kind of going into like, there is, this is why we did econ before this module. There's economic games that we put, like, we build these systems such that there is some kind of economic game or game theoretical approach that makes it so you're incentivized right? To play your optimal hand should be in the benefit of the network, right? And not against. So we try to always make the economic incentives greater for being a good participant, a good, honest citizen, right? Okay, next one, good. So I guess I'll go into it. Yeah, okay. Yeah, I'll go into it. That's fine. Proof of work cons, nice. Energy intensive. I mean, I don't know about you, but I kind of believe in the fact that just consuming a lot of energy somewhat wastefully, or in some cases not, as bad for the environment, but that's, I don't want to get too political up here, but I think that's pretty safe to say nowadays. A regular block time. This kind of sucks. So the thing is that when we talk about finding that pre-image for the hash, that we don't know how long that's going to take. We have an estimate of how long it could take on a particular set of hardware, but we don't know the exact time point that we will get a new block and transactions will be included and our state machine will be progressed. So a regular block time is not a great feature. Not so permissionless. Yeah, I guess I already talked about this one. I don't want to rehash it, but okay, this is a good one. So why do we even care about authoring? I think that's kind of like a good thing. I think the clear answer that probably a lot of people think is like, oh, I get some money, which that's one of the bullet points in here. But can anyone think of any other reasons why you'd want to do that? And maybe you've already read the slides, so you know the answer to this, but maybe you haven't. Sure.
Because you want to include your transactions?
Yeah, that's a great one. Like, I don't trust any of these people in the network. They all hate me. This is Joshi speaking, which nobody hates Joshi, but they all hate me, and so I'm going to run my own node and guarantee that even if they hate me, my transactions will get in because, you know, I'm running this node. So yeah. Another one, okay, altruism. Yeah, yay, SPF. So making the world a better place, you know, like let's all run nodes so we can all make sure that this network is alive and healthy and no government's going to come and bash it down. And, you know, if you think, I mean, I think this way still, that these systems that we're building do actually have some good impact on the world, then maybe it makes you feel good inside and you know, sleep good at night. Mike, yeah. Nice.
Saying like we can't like run an economy based on altruism because like we're thinking like in Mackenzian whatever classic economics, like it's supposed to be driven by selfish motivations, like because
Okay.
because like
Are you just saying like this isn't strong enough, like feeling good about yourself?
yeah, I mean because like once running a node costs like whatever, then like
Okay, so you're saying the economic thing is more powerful and this is very...
I'm saying like in classical economics or Mackenzian whatever term, like you don't like it's not driven by altruism, it's driven by selfish.
Okay. Yeah, I'm.
Because like you can't like do all the game theory and calculations and everything that we were talking about in previous modules with this assumption.
Okay, I get what you're saying.
You can monetize it.
I get what you're saying. It's not reliable, but it's a thing. Like well, but you'd agree that it's a thing because.
But once running a node costs like I don't know a few $10,000 for producing a block, then like at what point do you say okay, fuck it, like?
Yeah, I think it dives more into the behavioral aspects of things, which. Jonas is way
but that's
more.
Exactly why, like, we can't
third follow-up
on the stuff from before, like.
Yeah.
That's it.
I still think it's a thing. I don't know. My opinion. I mean, I mean, people do things against their economic interest, all for this bullet point all the time. Actually, if you think about it. I'll take one more. I think someone was like feeling excited and.
I think it's a balance between altruism and meritocracy.
Oh, meritocracy. Yeah, I love meritocracy. Yeah, we'll define that later. So let's go. Your transitions. Okay, so this is again, everyone hates Joshi, and so he wants to get his stuff in. And then money, right? Like, just give me money at the end of the day. Proof of authority. So yeah, so there's some other things. We talked about proof of work. Proof of authority is basically, so instead of just this kind of like, oh, whenever we solve the pre-image search for this hash, instead we just divide the time into slots. And then like basically certain people will just assign to each slot, right? And they, you know, by authority we mean, let's just go through all these then. By authority, we basically mean like you're some public key, or you have some key pair, and you can identify yourself that way. And we'll say, these 100 people, they're the ones that get to author, and they get assigned to slots, and only they can author. So no more just random people submitting their pre-image search. We'll just bound it to some set, and that's how we'll decide who gets to author. Okay, pros of proof of authority. So yeah, we don't have to do all this like extra work in order to decide who the block author is, and that might save on energy, which some would argue that's a good property. And then you have this stable block time, right? So as long as everybody shows up to produce their block, then you know that after X amount of time, we divided everything up into time slots, we'll get a block, and we'll get some progression in the chain deterministically. That's nice. That's a nice property for applications especially. Okay, am I talking too fast? A cons with proof of authority. So it's definitely permissioned. I don't think this one's debatable. That's kind of not the greatest property if we want this system to be open and kind of like open for people to participate and make it equitable. So yeah, there's no external resource like energy consumption to kind of like aid with this valuation of it, right? So the kind of nice thing is like, yeah, I don't want to go into that. Okay, that's fine. Incentives for honesty are not always clear. So the thing is say I'm a sanctioned person in the authority set, and I just decide like every time it's my slot, like I don't care, I'm not going to show up. Like, what are they going to do, right? That's kind of an issue. Like, maybe we should craft some additional rules in order to like punish that person or make them held accountable. So accountability is an aspect that we need to make sure that people are accountable to do their job, which is to come in and produce a block. Okay, some proof of authority schemes. We'll go through. Well, this one is popular, at least in our ecosystem, but I guess actually in many. It's a really simple one, but basically we just everybody just takes their turn in order, right? So at the beginning we just say like, all right, this person's going to go first, and this person goes fifth, and this person goes sixth. So the pros are, well, it's really easy to decide who's going to go next. And some cons are, well, it's not blind, right? I know that that's the fifth person's going to be, whose name do I know here? Sorry, Kat, sorry. The fifth person's going to be Kat, and so I'm just going to like take her offline because I don't like her and I want to kind of stall the system out. So that's not that great. Again, we talked about the blindness property being kind of good, right? In this situation, it's not blind, but it's very simple. So simplicity sometimes is nice when building our systems. And consensus systems can get actually extremely complicated. Yeah. Babe. Blind assignment for blockchain extension. I wish I knew the history of the naming, because there was an issue where I think so just spoiler alert, we have this grandpa is our finality thing. And at one point I think grandpa was like, I don't know, like the Reaper or something like that. And so they didn't want to have like the baby with the Reaper. Like that seemed kind of, so now we got grandpa with the baby. But anyways, and so, and Babe, blind is in the title. So in each slot, we compute a VRF output. If you guys remember from cryptography, we talked about verifiable random function. So in each slot, people can compute a VRF output. And if it's below some threshold, then you're actually able to be the one authoring the block. And let's go through all these. So if you are eligible, like you did pass getting a VRF, you commit to this VRF output, I should say that especially, then what you do is you submit your VRF proof and you can author the block. That basically you are the one who produced this value. So again, VRFs, if you don't want to recall from cryptography, they're a lot kind of like signatures. Actually, the internals works a lot like Schnorr. And how Schnorr signatures work. So it just you're able to basically provide a signature saying, "Yep, this is me." So I get to author block. Does anyone see an issue here, maybe, with how this works? Sure. Do it on time.
I'm not sure whether it's uniformly like everyone will get the chance like fairly or not with this.
Oh, okay. So, well, the distribution is actually fine, pretty good, but we would need to go more into the math on that. But yeah.
Maybe multiple people can prove that they are eligible to vote to produce a block at the same time.
Right. So the issue is that basically, so we talked about the fact that forks happen. These things are going to happen in the network, and we sometimes they're unavoidable. This is an important aspect of forks because there's this thing called a network partition, right? Where basically maybe I can't see what everybody's opinion is, and so the best view I have is what people I can see in the network and what their opinion is. But maybe it's not the overall consensus of most people's opinion. And that can be unavoidable because we have network effects, right? Where sometimes stuff goes offline and you can't see everybody. And these things just happen in networks in general. But in this case, so those are kind of unavoidable. We just assume always in consensus systems that this is going to be a thing that happens. But in this case, we're basically saying in our actual scheme, we say that you are eligible to author, multiple people are legitimately able to author. So when Joshi talks about finality tomorrow, you'll see finality, hint, hint, is one of the slowest aspects of achieving consensus. And you'll see why. Yeah, I'll just leave it at that. So we don't really want people to have multiple legitimate block producers, but it's a trade-off we're making to be more blind. Another thing about Babe is this is the way that we select the block producer, but actually this only happens about a quarter of the time. The other 75% of the time is we actually just fall back on Aura or a schedule, and that's because the amount of people that actually get to be a legitimate block producer gets to be too much. And that's a problem because we have these huge amounts of legitimate forks to go through and decide on. Sure. Mike, I know.
It says if it's below a threshold, right? So let's say the range is 0 to 10 and the value is 8. Then there'll be way more possible.
Yeah, you got it.
And then also why below threshold and not between two values?
Well, the threshold and how it's determined, I could show you offline. There's it's math.
All right.
Okay, cool. Don't make fun of me. Okay, sorry. We'll continue. So this is a bad aspect of Babe actually, and that's why we're ripping it out and putting a new authoring scheme in. And I'll show it to you as soon as we can finish this. Yeah.
You said the problem was that you get too many eligible authors. So
legitimate.
Legitimate.
Yeah.
So why not just change the threshold? Then you get less or more.
Well, okay. How do you change the threshold to do that? Yeah, that's what I thought. It's hard. It's not that easy. And we'll show. We had to completely create a new scheme. Because the thing is you're basically trying to say, I know how many random numbers I'm going to get below this threshold, and you can come up with a probabilistic answer, but there's no deterministic one. I for sure will always get 2 because it's random.
Isn't that what Bitcoin is doing more or less? Changing the threshold to.
Bitcoin does changes the difficulty if things become too easy, right? And they kind of. Yeah, they're trying to change the probabilistic time, basically. They don't want it to take forever, right? So they kind of will reduce difficulty and stuff like that. So yeah, but again, they can't say if I reduce it to this exact complexity, I will 100% get deterministic results. It's still probabilistic. One last question, and then I'm moving on. Was it somebody over here? Did they ask a question? No? Okay. I don't want to be mean to that side.
Yeah, Mauricio.
This is side wars.
Yeah, Mauricio. So concerning VRF in the epoch for like the slot for authoring block, right, and the babe. So one thing is what is the pseudo random you can say data coming from?
Yeah, that's a good question. So how the question is like, where do we like, how do we choose the input to the VRF? And we basically what we do is we treat like a concatenation of previous blocks hashes, because if you remember from the hash function hash lecture, we couldn't just know for certain like what we would get out for the hash, right? That was one of the properties of hash functions. We kind of got this like value, deterministic value out, but we didn't know exactly what it would be. So we basically use the block hashes and we concatenate them up for a previous epoch, and then we seed that with the VRF frequently to get our randomness. So randomness, spoiler alert, in blockchains is actually really difficult and a deep research topic. Not even just in blockchains, but in general, randomness is a difficult topic. Good question though. Okay, going on. Proof of stake. So we had this proof of authority thing, and so now it's like, all right, let's use econ to kind of solve some of the pitfalls of the proof of authority. So proof of stake uses like economic staking game to select authorities, and it tries to restore some aspect of permissionlessness to at least proof of work levels. That's a thing. Yeah, we like proof of work and some aspects of proof of work again. So again, we are trying to solve this permissionless issue, and so we use this proof of stake way to kind of achieve that. Restores clear economic incentives. Yes. So there's many ways to do this, by the way, and like exactly how the staking system works. For instance, like in some consensus systems, Solana, there's an ability for basically for you to always choose the guy pretty much who has like the most stake on their node. And that kind of resolves in the fact that you have a single leader for longer, which is nice again for performance, but bad for the properties that we talked about. So there's ways to kind of spread the love and ensure more fairness. And again, we want this thing to be rotated. And I guess this is just a general thing to say about a lot of these blockchain systems. You know, it's always sometimes difficult at the beginning to tell which ones are better for what reasons. And you just, you know, you listen to your friend and they're like, I really like this thing. And you're like, okay. But when you actually analyze it, you see under the hood that people make a lot of these trade-offs, right? So like performance, a lot of times gets traded off for security properties. And it's important to know when people are making those trade-offs, when you go like, oh, this thing doesn't scale enough or whatever, and you're like, well, it's actually really secure protocol though. You can't really break it in many ways. You have to kind of value your block space or your blockchain based on these kind of aspects. Yeah, that's a distributed systems things that Vitalik ripped off, put his own thing on it. I like Vitalik though, I like Ethereum. Okay, so yes, so this is important to make note. So a lot of times we like kind of like, I would say for the most part, I know that it says like sometimes, Joshy, but for the most part we do have some coupling involved in the actual state machine and the consensus system. So one example is like, who is going to be the authorities, right, that we listen to initially? Where should we put those, right? And a nice way is we commit to them on chain, right? And so we're actually able to validate at every change in every new block who are the authorities who can author blocks, for instance. So there's a lot of times, or maybe they have, you know, we pay them on chain, and so if they misbehave, we can punish them on chain, and we can verify that on chain, where everybody can see that this guy was actually being a bad guy or bad girl, whatever. And so there is a lot of times coupling between the consensus system and the state machine. So yeah, it kind of says there, block reward slashing authority election. And this kind of talks about how there's, yeah, in Bitcoin or in proof of work, generally there's some adjustment in the algorithm that happens. Okay, little hint to the next section in Substrate. There's an API that you can access basically from, this is, all right, I won't go too deep on this, but there's frequently, from a programmer's or dev's perspective, there's a way that you can like go into the blockchain area and check. Like generally we say like the stuff that's on chain is like a safe space, right? Because all of the consensus participants are able to really validate what's going on in there, and they've agreed on it. And if so, that's generally like your kind of more truth zone, I would say. And so in Substrate, which is the blockchain building framework that we use, there is basically just an API where you can go in and find these things out, what's happening on chain, off chain. Yeah, we'll get there. Okay, fork choice heuristics. This is important. I talked about it a little bit. So there's different ways which we choose which opinion we want to choose. And these are some of the ways that we decide on it. So one of them is longest chain. So like, okay, I tried to tell Joshi like, hey, this is actually the right fork, bro. And then he's like, why is it so small? You know? And then I don't know where I'm going with that. And so we choose the longest chain because there's been like more legitimate blocks maybe have been built off of it. So this is one way that these heuristics that we talked about of how we choose. And a lot of attacks actually exploit this heuristic by trying to do stuff like build an alternate fork that's really, really long and then convincing everybody, hey, this is actually the correct state. And if you think about it, it could be kind of bad, right? I could just like fake all of the transactions in that whole fork. So being resilient is not being able to do this very easily. Most accumulated work. So this is like one, I think, in Bitcoin, where you have like, okay, maybe it took like not a lot of search time to actually find the pre-image for some specific hash, and that gets like kind of a score, but maybe someone spent a long time finding it, and we will weight that accordingly. So anyways, just another kind of longest chain type thing. Or maybe we just care about Alice, and we're just gonna say we're gonna just follow the one that Alice is authored most on because I like Alice, and she's cool. Yeah, or most total transactions, most gas, like miners are selfish, right? And we can kind of weight it that way. Anyways, reorgs. I guess Josh, you covered this a decent amount, but we can just talk about it a little bit more. So yeah, so maybe, I guess, first we're following this top chain, which, like, you know, here we have a fork, and we're doing longest chain, so we're following this, and we think this is the correct, we're choosing this one to follow. This is the opinions that we've seen so far. But then all of a sudden we realized that we were kind of partitioned from the rest of the network, and we find out that actually this one down here is the one that we actually want to follow. So we basically have to go back and kind of go backwards. So from the state machine example, we remember that like I have a transactions here, and that changes the state of my state machine. And then we have another list of transactions that come in, which change me to this state. So you basically have to kind of do the reverse there, where you say all the transactions I got here, let's throw them back into that transaction pool, and so on and so forth until we get back to the area which we're reorganizing on, and then we go forward that way. So sometimes transactions can kind of get a little bit, I won't say lost in the ether, but it's possible, right? Like generally they'll get picked back up in some amount of time, for sure. Yeah. Irving. Keep up your energy's hard, Joshi.
Just a question. So, in the context of a fork, there is a threshold, right? I guess in terms of one, the number of nodes that are telling you that they've seen a different block, and also a threshold, I guess, between the number of transactions that are different between the block that other people are telling you?
Well, like you're asking a good question is like, how do we choose? It's basically how to choose forks. And I would just say there's many rules for how we could do it. Those are some good ways as well to kind of to choose. All of it is so that we can build up to really get an honest viewpoint of the chain. But it varies. It varies a lot, actually.
Okay, thank you.
Yeah. Sure. And let's see. I kind of want to, yeah. Let's see how much time I have left. Yeah, I want to get to Sassafras.
How do we do the reorgs? Like, do we have multiple copies of the blocks state at different block heights? Because like just doing the inverse of operation and going back, like some inverses are really hard to compute.
Well, okay, so generally, generally, in the ways that I've seen it, and I've had to build some consensus pieces of protocols. So you have this thing called a fork tree, and you basically put everything in a tree structure. And so if you think about it, this is like child whatever, and this is child whatever, and this is like an ancestor node. And so what you do is you actually like can basically you hold a lot of these ancestor nodes around until you do a reorg and you get some pretty good guarantees that this really is going to be like a node that you're going to follow, and then you can kind of prune its siblings a little bit, right, and just take them out of the tree because you know you're not going to follow that.
So you have redundant information until some finality.
I won't say finality yet, but yeah, that generally, in Substrate, when you prune a lot of the fork tree, then it's based on like this node being finalized. But we'll talk more about that. But it's not as hard as actually you think. If you just hold some stuff around from the past that you're unsure about, you can then kind of act on it quickly. Okay, yeah, so this is what I said. They'll re-enter the transaction pool, and they will reappear in blocks. Sometimes they can kind of get a little bit lost, though. Oh, double spends. Yay. Cheating. So we can kind of exploit this fact of this reorg if we're not careful. And you'll notice some properties of things like exchanges, which take extra precautions so they don't get screwed by this. And so one might be that, hey, I'm following this fork at the moment, and I pay somebody. I like Josh's example, buying a car. So it's like, I paid you to buy a car, and then I just drove the car off the lot, right? And then there was a reorg, and actually, this is a totally invalid fork, and we go down this way, and I basically didn't, I don't pay you anymore, right? So it's like, thanks, I got the car, and so what a lot of like exchanges do, because in something like proof of work, there's just a lot of forks all the time, and so you probably have noticed if you've ever used crypto, like you're like, why is this exchange taking so long? The blockchain's faster than that. They're just waiting a significant amount of time to make sure that they're past the point that they could reorg the transaction. Cool. Okay, yeah. Pay counterparty, pay friend. Okay. So yeah, I think this is the beginning slide. So we basically went through all of these, and tomorrow we'll talk about finality in depth with exercises and everything. And you'll have all the finality out of you by then. So I have another thing for maybe 20 minutes to go through Sassafras. It's like a very novel one. It's being implemented now, and then I guess we can break for lunch. Is everybody okay to do that? I mean, yeah? Okay. All right, cool. Let me get that one up. So it is right here. And boom, Sassafras. Oh, okay, breaks. So yes, we have this problem with Babe. And what we want to do is be able to tackle a lot of the problems with Babe. That's why this scheme was came about. Oh, let me get my speaker notes up. Oh, sorry. 2 seconds. Oh. Let's take that away. I don't want you to see that. Come on. Oh, dude. There we go. Okay. Oh, unable to. That's great. Nice. One second, technical difficulties, I guess. Let's close this one. Oh, great. That's nice. Yeah, I'm going to check that right now. I think it's not. Okay, so we tried to address this problem, and this is being implemented now, and yeah, I think it's pretty cool. So we have sassafras semi-anonymous single leader election, and I'll show you why we say semi-anonymous in a second. But does anyone know what sassafras is? Just a question. Sure. Oh, sorry.
Yeah, I'm Risha. I know a little bit about it. I was following discussions.
Oh no, I meant the actual
yes
sassafras thing, not the.
Okay. Yeah. So yes, the issue is concerning Babe. There's a small set of validators.
Oh no. This has nothing to do with blockchain.
Oh, the long form sassafras.
Yeah.
I don't know.
Oh, okay. It's a tree. And some extract for that tree is used to produce something that people like in parties. I'll just say that. So, not saying we named it after that, but maybe we did. Okay, so sassafras. But don't we have Babe, right? Why replace Babe? Babe's cool. So we talked about this. Forks are legitimate, which makes our stuff slow. Why is forking an issue? I basically answered this, or we answered this together. It slows down, especially finality. And this is an aspect that actually, like, a lot of people don't even realize, is that we're not even using Babe for most of the time. So we're falling back on Aura, and that's bad. Okay, why is this an issue? We talked about that. Okay, so can we do better? This is sassafras. Nice, beautiful tree. Yes, I was really excited making this. Okay, so what are our goals again? We basically want to reduce to no forks. Again, I talked about that, the fact that, like, we will have some forks because some people just generally are confused. Even if they're honest participants, they're generally confused. This is kind of unavoidable in our current networking assumptions for P2P networks and networks in general. We want to make slots anonymous, so not known ahead of time. So we talked about this. And we want to go fast. We want to be secure. We talked about the value of block space. We want things to be secure, live, all the properties that we talked about, and also pretty quick, right? Like, we want our systems to go fast because we're all super impatient human beings. Okay, so we need to revisit basically 3 things. So the main magic of sassafras is really these 3 things put together and some cool things that some smart people came up with. And so ring signatures, VRF, and the ring VRF, which we barely touched on ring VRF at the end, but this is really the magic of the whole thing. Okay, ring signatures. So what are the properties of ring signatures that we really like that are used to basically craft the ring VRF? So for a group of size n, we can create an anonymous signature from within that group, right? So we can know that from somebody from n produced this signature, We can guarantee that, and we can guarantee that it's only one of them too. That's very important for this. And so what does that mean? It means we have a valid signature, which we can verify, but we can't identify which secret basically signed the message. This is a property that's very, very good. So does anybody know what we're I think maybe we talked about this, but what we're giving up property-wise to achieve this? We talked about these properties like authenticity and stuff like that. Non-repudiation, right? Because we can come to somebody and say, hey, you're one of the ring participants, you signed this, and you can go like, no, I didn't, I don't know, you can't prove that. So we're trading privacy for this non-repudiation property. VRF. So the VRF, so for some public input seed, again, we talked about a lot of times it's like previous block hashes added together. And some secret, we can produce some random output, and we can verify. And we can submit a VRF signature, we call it, but it's VRF proof, that we possess the secret that generated the random output. That's an important thing as well. So for ring VRF, we basically just combine all, it's not so easy to just combine them, but we use some zero knowledge proofs in order to combine these things together. So the main thing that is important for Sassafras, though, is that we have some VRF output, which we've generated with some secret, but we don't know who generated the random output, right? And that's really nice, and I'll show you why. And then, yeah, we can also submit a proof saying that, yes, this was indeed us from the ring, right? Not somebody else, but somebody from the ring participants. Okay, so why is it useful? Well, I just said it. Sorry. Okay, so this is a kind of an important thing. Nice. Thanks, ChatGPT. So if we're talking about this block authoring stuff and consensus participants, who do you think would be the ring participants then? Does anybody have a guess? I haven't heard from the orange hat person. Ever. I'm really interested. Yeah, sorry. But spread the love. I don't want to do aura for the whole class. Maybe everyone doesn't want that.
Validators?
The validators, yeah. So the ring participants, the people who would be signing these things or producing ring VRF outputs are actually the validators. Cool. Tickets. All right, cool. So we have this in Sassafras, we're using this term tickets. Nice. So what's a ticket? Well, a ticket for a lottery. The lottery being, yay, I get to participate in consensus. So we have to select the people who can produce blocks every time. So we talked about proof of authority where it could just be, okay, these 100 people, they can always do it. And then proof of stake, maybe there's some money aspect in there as well. And the thing is that maybe there's only a limited number of people who can author in a particular epic, we say, or session. So what we have to do is kind of pick from the greater pool down to a smaller pool of people who will get to author. Okay. So we say a ticket for a lottery. So each participant creates a ticket. So actually a ticket in the context of actually what it is a ring VRF output. So somebody will actually compute this ring VRF output. So when should we create a ticket? This is kind of a question I have. And this may be not super obvious, but if we're going to create a bunch of tickets in order to submit them and maybe get chosen to be in the consensus round, when should we actually compute this ticket? Like at what time point? Does anyone have an answer to that? Oh, orange hat again. I'm being biased now.
Just a trial. When we have maybe several validators who want to validate at the same time.
Well, that's a good thought, but we kind of assume that like a lot of people want to validate. Like there's no shortage of those people that we want to get money. I love money. I mean, not that much, but I love money. Yeah. Yeah, Mauricio, and then we'll continue.
Oh yeah, in the epoch slot, the allocated slot whereby one should be selected to produce the block in that period.
Yeah. So at some point we need to decide who are going to be the people who are going to author, right? And so basically we should probably do that before. I mean, in this case we do it before because we want to assign each people in the lottery to a particular slot. And so we need to basically do that. We say an epoch before we need to decide this. And because we get this blindness property, we can really kind of do it in ahead of time a decent amount, actually, securely. So we do it before. Oh, did I? Okay, did. Okay, so submitting a ticket. So we created this ring VRF output. Now we need to submit it an epoch before so that it can get assigned to a slot, maybe if we win in the lottery. Each participant computes and submits their ticket on chain. Any problem with that that you see? I'm seeing if anybody else besides Mauricio, but I will go to you, Mauricio. Yeah, so again, the question is, each participant computes their ticket and submits it on chain. The hint is there. You know who submitted it. Someone yelled it out and stole it from the, yes, but yeah, it's okay. It's good. Is that what you're going to say? Yeah. So that's a problem, right? Because if I'm trying to be hidden and I submit this like ahead of time, then they know who I am, right? And then if I get assigned, if this ring VRF output gets assigned to a particular slot, say slot 10, then I actually do know who it is. So we have to solve that problem. Oh, yes. So the answer is the anonymity is broken. Should I put here? Okay. Okay, so the question is actually, I don't know why I didn't put in the slides, but there's a solution that we have to that. Can anyone think of a solution actually? How we would solve that?
No, I can't. But I do have a question.
Oh, okay.
If they compute the ticket and put it on chain, isn't that like a kind of endless strange loop where they've got to get a block to put it on chain? So
well, that's fine if they do. We just do it we do it before. We do this before we're going to ever, like, for the next set of validators who get selected to produce blocks. So, and this is very, I guess, Polkadot specific, but there's an epoch is like some period of time which certain validators get to produce blocks. And then at another point, we want to be equitable and allow other people to get in. And so we select a new set of validators and the next epoch, basically, for some period of time. So we just do this beforehand. It's fine that they're on chain, it's just beforehand. But I mean, so my question is specifically, how could we fix this like submitting your own ticket issue? Okay, Irvin or, yeah, okay. Well, Mike's already gone there.
Could be a simple commit and reveal scheme.
Perhaps. Okay, I'm not really sure. The thing is that if you commit, you're still identifying that it was me because I signed the message. Whenever we submit something on chain, I guess this is a spoiler, like we sign the message so they know it's us.
I have some ideas, but I'll let someone else chime in.
Oh, okay. Okay, so it's kind of a simple answer actually, unless somebody had a, yeah. We just send it to our friend, right? And we just say, hey, can you post it actually? So that's the, it sounds, it's not, it's actually, you know, what would be ideal maybe is if we sent it to a friend and then that and it was encrypted and maybe only the next person maybe could submit it and then we could preserve some of our anonymity, but that's like super hard to prove. Because in these networking scenarios, and maybe we talked about with peer-to-peer networks, like things can get, it's very hard to prove somebody got something, like a message or a transaction, because they can always just claim that they didn't get it and, oh, maybe I was offline. So we just send it to a friend and we say, hey, can you please post it? And we give them some economic incentive. And basically we pay them. And the fallback is like if the person maybe we generally send it to the same person because they're pretty creditworthy. But maybe if that person becomes uncreditworthy and doesn't post our ticket, then we can just post it ourselves. But then we break our anonymity. So honestly, this is yet to be seen how this actually unfolds in Polkadot. But I assume we'll just make the general, when we have problems, this is kind of a nice general theme. When we have problems in consensus or blockchain security, we always go to economics. It's like our fallback of like, let's just make it incentivized with money, basically. Cool. So we sent it to a friend. Sure, I'll take one more, but yeah, I'll try to get you out of here by 1.
Even if we send it to a friend, isn't it traceable back to us, right?
The friend knows.
Yeah, but it's on chain, right? We're sending it to a friend.
No, when you send it to a friend, you send it offline. So the thing is that they can still verify the proof themselves locally, but they don't need to broadcast it to anybody. You can just send it directly to them. You can encrypt it and just send it to them, basically. Or only they can. Yeah. I'll take one more.
Incentive could be monetary in crypto land. So for the blockchains that are not dependent on crypto, what would be the incentive there?
The blockchains that are not dependent on cryptography?
Like that are not money related blockchains, right? So
oh, you mean just in general and like how you secure them then economically?
Yeah,
well, I mean, this is kind of a property that we generally have of most systems. I don't know if there's a example.
Let's say it's a health organization or something, right? Like all health records are safe. But then what would be the incentive there of assigning tickets to a slot where it could not be related to money?
Well, this is specific for Polkadot, which we do have money involved. I mean, we could think of some other schemes, but in general, like we operate on this premise when we're designing our protocols that we can provide economic incentive in such way. Like, actually, the whole protocol would break without that.
Yeah, and I do want to remind you that yesterday I told you I love you, but Joshi, we love you too. It's the hair, it's the System 76, and it's the tie.
Oh yeah, it's hard to be Joshi, so please be soft on me on the feedback forms. Okay, so once we've submitted tickets, we have to assign them to slots, right? So we've all computed our Ring VRF outputs. We've sent it to a friend. They posted it because they're cool. They got paid, and then we need to say, okay, we have a bunch of tickets. How do we decide which ones get picked and assigned to slots?
Question over here. Sorry. My question is, if you're still sending it to a friend, who's to say your friend isn't like yourself? He's still signing it, right? Why cannot you just like take the role of the friend yourself?
You can, but then you're gonna reveal yourself.
But couldn't like the fact that you have a friend already reveal that?
Well, there's somebody in the authority set, but they don't have a way of revealing you, so to speak. I mean, I guess they can if they don't post it, but yeah, again, you can reveal yourself, but then you're giving up your anonymity, which makes it more likely that you could be tampered with, basically, in the process.
And what about the friend? Wouldn't he also fall like victim or like probably be looking to the
well, the thing is that you can't prove, again, like with this networking thing, you can't prove that he didn't get it. He can just say, I was offline temporarily, I didn't get your message. That's always the underlying networking assumption that we have to kind of operate on. There's ways, very like advanced techniques to try to find ways to handle that, but that's generally, this is like the best we got. And we just assume that if we economically incentivize good enough, then he's probably going to post it for the most part.
I got you.
I'm going to go on and I'll just take questions at the end. I'm almost done. And, yeah. Okay, so we need to assign tickets to slots. We want to prevent someone from finding ways to manipulating the randomness. This is important. This is like a whole talk on its own. I plan to do it the next one. Sorry, you guys got messed up on that. But and I'll kind of show you a little bit what we do to avoid that. So the question is, what can happen if a bad actor can get a majority of the slots for an epic? I think we can kind of all see that, right? If you can find ways to get all your tickets into the lottery and you're a bad guy, you can do, well, you can even snowball your influence on the network over time. There's a nice, I'll probably link, there's a nice talk about how Ethereum addresses this and how they document it. But basically, again, this protocol, Sassafras, is very reliant in security model and many consensus authoring schemes on randomness being good. And so there are some of the best ways to attack consensus systems is if you can exploit the randomness. So so if a bad guy can get majority of the slots, they can get all the money, but then they can basically lie about the network in a big way, and that's scary because then they can basically mess the whole network permanently, almost. Okay, cool. So how do we address like who gets tickets, right? So we use this like outside-in assignment, and it's if you think of if we had ticket 1, ticket 0 through ticket n, this is the way we sort it, and so we put ticket 0 at the end, and then we put ticket 1 here, then we put ticket 2 at the end, next slot, and we put ticket 3 here, and so on and so forth, and kind of build inwards. And the reason is that if you can find a way to get, if you don't kind of do this, and you can find a way to get multiple consecutive tickets, then you can do this thing where you have big influence over the network as a bad guy. So this kind of prevents and breaks up people who can get a lot of consecutive tickets in a row. So because when we seed these VRFs in general, we use the randomness from previous blocks. If you get a lot of the blocks, if you're the person who can produce a lot of consecutive blocks, you can like strategically try to choose the randomness. And that can be bad because that depends that randomness, it decides who gets assigned on the next epic, right? So if I can influence the randomness for the next epic, I can kind of snowball the randomness attack, and it's bad. So we do this outside-in assignment of tickets to slots, and then we kind of just like chop off at some point because we don't have as many slots as there are tickets. Okay, and then at some point so how do we prove that it's our turn? We have slot X coming up. We want to say that it's us. We want to produce our block. So we submit our unique VRF signature / proof, and that's able to be verified by everybody. And then we produce the block. So, summary. We produce the ring VRF output, the ticket, 1 epic before. We send it to a friend. They post it on chain, hopefully. If not, we do it ourselves. And then outputs get assigned to slots. It's outputs here being tickets. Randomly, pseudo-randomly. And then when it's your turn to submit, you submit your VRF signature proof, and then you build your block and get your rewards. So I think I made 1. Oh, perfect, 1. So yeah, that's pretty much it. If anybody has any questions, then sure. Okay, I'm gonna go this way and over. So Jess.
Yes. So you said tickets get randomly assigned, like the ticket gets randomly assigned, and then is it like, do you get informed that you have the ticket and then you submit your VRF proof? Like, is it?
Yeah. So at this 1 epic before, the tickets are on chain, and there's logic that assigns you to a slot, and you'll see which outputs correspond to which slots. You'll know that yours is slot 7, for instance.
Then you send it to a friend. The friend posts that on chain.
That's before, yeah. Before you create your ticket, that's your ring VRF output, and then you send it to a friend to post it on chain. Okay. After everybody's tickets are collected on chain, it does the sorting, and then it assigns the slots.
Okay, and then the slots are figured out, and then it's your turn to submit.
And then when your slot's up, it's your turn. You submit your proof.
But not everyone gets a slot.
Not everyone gets a slot. Sometimes there's more tickets than there are slots, and there's some randomness to decide which tickets get assigned to slots. Yeah. I'll do Rishi, and then we'll go to Vincent, I think, right? Thank you, Vincent. Rishi.
Sorry.
So, technically speaking, I could be my friend.
You could be your friend.
Okay.
I mean, I could be my friend too. I mean, yeah.
Yeah,
That's always possible, right?
In the context of like sending that.
Yeah, you could be your friend, but you would break your anonymity. That would leave you vulnerable.
Okay. Okay. I'm gonna ask you.
Sure.
Maybe
Yeah.
later.
Yeah. We can.
And, just a follow up.
Oh,
just
sure.
Out
Yeah,
of
one
curiosity, who comes up with these names? Babe, Grandpa, Sassafras.
You'll need to meet that person eventually. He'll be around. He kind of just wanders around.
Okay.
We have his name is Jeff.
Okay. Cool.
He's the name guy. And many other guys. He built a lot of the crypto primitives. He works at Web3 Foundation that we have. And he's, we sometimes, I don't know, we'll have like 15, 20-minute discussions just on names sometimes. Okay. And it's all about how can we laugh the most, usually. But yeah, sorry. Yep.
So when you get to step 5, are you just like, so you do step 2, you send to a friend. Are you just delaying the inevitable when you get to step 5? Because you still show that you submit something at the end of the day, right?
Delaying the inevitable? What do you mean?
Like, you send it to a friend, so you don't show that you have a ticket. When you get to step 5, you submit your VRF signature proof.
So if you would, if you submitted a ticket to a friend and they didn't post it, that's the question. But you still submit a proof?
No, so like, the point of sending it to a friend is to hide your identity, right?
Yes.
But if you get to step 5, your identity is still revealed, no?
Yes, but that's when you produce the block. So that's when you want to reveal your identity, right? The whole point of keeping anonymity up until that point is so that nobody has time to act to hit you, basically, and attack you.
Makes sense.
Yep.
Yeah, so I have two questions.
Oh.
One concerning sending to a friend, right? Okay, your friend also, the transferring message passing of the tickets to a friend, is it like same as gossiping blocks, like the same thing?
The actual implementation of how the message gets, yeah, I think that it is. I have to check I think that they are using that. Basically, you can choose who you want to gossip it to, encrypt it to just so they can decrypt it, basically.
Okay. So second question is concerning the forkless. Okay. Forkless thing which comes with Sassafras, in a way that it is less probabilistic to kind of get two people assigned on the same slot, right?
You actually, it's deterministic on one ticket per slot. Yeah.
So no clashing, no.
So the question I think really is like, are you sure that like someone couldn't create like two tickets, the same person, but when you verify the ring VRF, you can see that it's one specific person. So even though you don't, I know this is really unintuitive, but even though you don't know who it is in the ring, you know that it's one person in the ring.
Person. Okay, okay. The final thing is the whole we in the active validator state, maybe we are 10 validators, right? In the active validator state. And are we all producing tickets and then waiting to be assigned, or after one epoch has ended and that like the short period of time, we are kind of pre-selected, like maybe 5 of you need to submit the ticket, then 1 of you will be chosen in the next slot, or like all validators in active validator state are selected?
I would need to look at the implementation. You could do it either way, actually, but yeah. So you need to kind of pre-select who's in the ring, right? How we rotate, I need to go check at the implementation. So if you're interested in this at all, there's a long PR and RFC with the fellowship, and I can show you all the resources. And the person who's really implemented it, this guy Davida, he has like everything like meticulously out with checkboxes. So you can look at every checkpoint step of the way, basically.
Thank you.
Okay, I'll say 2 more and then we go to lunch.
Can you post that link in the Discord, like with?
Oh yeah, I will. I'll post all the. Yeah, I meant to put that in my slides, but sorry.
I had like a few questions, but if that covers everything within those materials, then I'll just pass the mic.
Yeah, there's a lot of details there. It's all. There's even a paper, by the way, I should say. Like we published a research paper. So if you really want to get into the math of how the whole protocol works, we have that as well.
So you gave a brief explanation of what a ring VRF output is, and then you equated it to a ticket, but I never understood what value you get out of the ring VRF.
Okay, so the value, I think sum that up pretty simply. So VRF allows us to produce some random value. Good. The ring allows us to, and so if we take away the ring, and we just talk about the VRF, basically you have a public key associated with a value. That's kind of like how this works. So you could submit a signature saying, I produced this value. That's good, but that identifies who you are. Okay? So in order to get anonymity, we throw the ring aspect on there so that you know that this output is belonging to somebody in the set without knowing who it is. One person in the set. So the value is that I can randomly produce some value, and it can get assigned to some slot, and then eventually I can prove that it was me actually. So does that make sense?
Yes, but does that mean that inside a ring there's a bunch of validators that are internally competing for a slot?
They are. The way that they get chosen though is by this lottery system basically. So they don't know, unless they know how to exploit the randomness, if they're going to get selected for a particular slot, but they just submit.
No, not a slot. A ticket is, well, it's a ring, right? So there's a few people there. One of them signed, right?
Yep.
But there's a few validators there. So what's happening internally? Like maybe all of us are in one ring and I sign it every time. What about the other people?
Well, the other people are going to sign. They want to produce blocks.
That's the mechanism I'm asking about.
Huh?
That's the mechanism I'm asking about. So,
I'm confused. What mechanism? Like exactly how the ring VRF works?
After step 1, you kept talking about ticket as representing one person.
Yes.
The ticket is representing n persons that are in a ring.
Yes.
One of them signed. What about the other n-1 people?
They also produce tickets. Everybody does this.
But then the ticket is selected.
Then eventually the ticket is assigned to a consensus slot.
Based on a lottery. I'll come privately. I don't understand.
Okay. Sorry. Cool. I guess we go to lunch.